Hi, everyone. After today's lecture, I thought it would be useful to you before I filed away these notes to record a short video to show you one more time how the Lac operon works and how the trip operon works. So let's start with the Lac operon. Remember, all operons have regulatory sequences, promoters, and operators in this case. The promoter serves as the binding site for RNA polymerase. The operator serves as the binding site for the repressor. The operons also have regulatory proteins. The regulatory protein, which in both the Lac and Trp operon are repressor proteins, are coded for by this regulatory gene. And then operons have structural genes, which are also coding regions, which code for the enzymes that serve the purpose of that operon. So let's talk about the Lac operon first. First, RNA polymerase comes along, binds to this first promoter, transcribes the regulatory protein gene. The mRNA that is transcribed from that gene is translated, and a regulatory protein, a repressor protein, is produced. Now, in the Lac operon, that repressor protein can immediately bind to the operator all by itself. It does not need help. So RNA polymerase binds to the next promoter, but it now cannot do anything because it is blocked by that regulatory protein. So in this case, the Lac operon, in the absence of lactose, is off. Now, let's say I throw some lactose in the mix. Lactose functions as an inducer molecule for this operon. Lactose actually binds to the regulatory repressor protein, changes its shape, that changes its function so that the regulatory protein can no longer bind to the operator. Okay, now that lactose is present, the regulatory protein cannot bind to the operator, so RNA polymerase is free to transcribe these structural genes, which make enzymes that digest lactose. Remember, the function of the Lac operon is to make the proteins that digest lactose. So once all the lactose has been digested, the regulatory protein snaps back in shape and can bind to that operator again and turns the Lac operon back off. So remember, the Lac operon is catabolic. Its default setting is off in the absence of lactose like this. Okay, and the regulatory protein for the Lac operon can bind to the operator all by itself, and the molecule lactose functions as an inducer molecule. So that's the Lac operon. Now let's talk about the Trp operon. Same basic structure. You've got regulatory sequences, promoters, and operators. You have a regulatory protein gene that codes for repressor, and you also have structural genes that code for the enzymes that do the job of the Trp operon. Difference here, Trp operon is anabolic. Its job is to synthesize or produce tryptophan. So here comes RNA polymerase, binds to this first promoter, transcribes the regulatory protein, just like it did for the Lac operon, but it's a different regulatory gene, different regulatory protein, and it makes the Trp repressor. Here's the key difference. The Trp repressor cannot bind to the operator by itself. The Trp repressor cannot bind to the operator by itself like the Lac repressor can. So RNA polymerase can bind to the second promoter. It has free reign because nothing's on the operator, and it's free to make the structural genes that code for the enzyme that synthesize tryptophan. So once it does that, these structural genes code for enzymes that make tryptophan. Now we have an excess of tryptophan. We have too much tryptophan. We don't want any more tryptophan. So what happens? Tryptophan acts as a co-repressor, which is why the Trp operon is called a repressible operon. It binds to the Trp repressor, changes its shape, so now the two of them together can bind to the operator. Now RNA polymerase can't get past the promoter, and the operon is turned off. which makes sense because if you think about the needs of the bacteria, you would want the trip operon to be turned off when there is plenty of tryptophan because you don't need to make any more. Anyway, hope that makes sense and have a great day. Bye.